So in this video, we will discuss about energetics, especially calculating pole energy and also understanding exothermic and endothermic reaction. So first, energetics. So we deal with chemical reactions and also the energy that is released or taken in by the chemical reactions in order to fulfill that reaction. Typically, if we would like to transform something, a reactant, into a product through chemical reaction, we will require some kind of energy, whether it's like light energy, electricity energy, or heat. And then, in terms of energy, some would be taken or some would be released. So, from energetics point of view, we can classify reactions into two, which is exothermic and endothermic. Let's say that we have a bigger glass full of a liquid, a solution, and we put a thermometer. Let's say that initially the temperature, thermometer reading is 25 degrees Celsius. And then after some time, the reading would read, let's say 32 degrees Celsius. So it means that the solution actually releases energy so that the water temperature increase. In this case, the solution or the chemicals we call as the system, while the water and the surrounding we call the environment. We see here that the system causes the environment temperature to increase by 7 degrees Celsius. Therefore, we can say that the system releases energy. So we could consider the system to be exothermic. So in exothermic reaction, the system or the chemicals that we discuss will increase the temperature of the surrounding by releasing energy. And that energy will be absorbed by the surrounding. If it is the other way, so like the temperature decreases instead, it means that your reaction, in order to happen, requires energy. So for example, if it is the other way around, yeah. So solution, then it goes from 25, let's say, to become 17 degree. So in this case, the energy in the environment is taken by the system. So energy taken by the system to conduct the reaction. So that's why it will feel colder here, while the system itself actually will gain energy. What's an example of endothermic reaction? So this is what we call endothermic reaction. Such example would be like when you put alcohol on your palm, and then after some time it would evaporate. Then your hand would actually feel cold. Why? Because the heat from the palm is actually taken by the alcohol so that the alcohol can evaporate. Okay, now let's see this from energy level point of view. So let's say that we have two graphs. Yeah. Total energy of a system at one time is called enthalpy. Enthalpy. All things should have a certain potential energy, like they have specific amount of energy stored within them. For example, like wood. Yeah, wood, you can burn wood, right? And then after you burn wood, then the wood will release some heat, and then you can use that heat for cooking or for warming your body. But wood as itself, yeah, it cannot do anything. It just stays there. But we know that if we burn wood, it can turn the structure into valuable source of energy. It means that wood has a certain energy level, right? Let's say that it's at this point. Yeah. This is as time progresses. Yeah. Time progress. This is the enthalpy or the energy level. In order to do a reaction, actually, we need to supply them with energy. So of course, from the initial condition, so initial condition, Because of the increase in energy required to start the reaction, the energy will jump, the energy level will jump. Now, the thing is that after the reaction, what will happen? So the reaction will form a stable product. Now, if the product level of energy is higher, let's say this final, it means that your final product has absorbed some energy. But if your final product energy level is lower, let's say this, it means that your final product has lost some energy. By how much? It gained by this much. So this is what we call the change of enthalpy, the change of total energy by the system. So in this case, the final position is higher than the initial position. So the delta H will surely be positive. This is the trace of endothermic reaction. While this one, the final position is lower by this amount. So the delta H will surely be negative. This is what we call exothermic reaction. Now, if you see from the graph, from the initial condition, it reached a certain peak. And this peak is actually the level of energy that must be achieved in order for the reaction to conduct. If this energy is not achieved, the reaction will not good, will not progress. So this here we can label and we call activation energy. So from the initial position to the highest peak, EA or activation energy is the minimum energy required to start a reaction. So this should be the complete label. The initial represents the reactant form, while the final represents the product form. Okay? So it's actually easier for us to track changes of energy compared to putting exact number here, because it's very difficult for us to calculate exactly the whole energy contained within the system at this point. So it's actually easier for us just to track the changes. The endothermic would have higher final position compared to initial position. You can also think that, for example, you want to start a business. Then this is your initial condition, your initial position. Because you want to start a business, you need capital, so you borrow money from the bank. Let's say that you borrow 1 million. So then your money will increase compared to initial position. After you run your business, it turns out that the capital you only need around 500,000 from 1 million. So compared to your initial position, you're actually still surplus 500,000, right? Because you borrow money, but you only use some of the money. But for exothermic, you borrow money to start your business, but you use even more than your loan money. So you have to even take out your saving. You will start your business as a negative position. So that's the difference. In order to start a reaction, energy must be supplied. Energy supplied. And then it is used actually to break the bonds. To break the bonds or to break the pre-existing bonds. Because like in any chemical reaction, for example, like let's do simple one. They have a reaction here. Becomes ammonia. So we have to balance always. Okay. We have nitrogen, let's say. Then we have 3 hydrogen. But then we have 2 NH3s. If you see, the arrangement of the atoms are different, right? So in order for the reaction to happen, we need enough energy supply to break all of this. To break all of this. And then arranging them into this shape. After we arrange this, any leftover energy will be released. So that's why making bonds will release energy, while breaking bonds will take energy. We can also predict that a reaction is endothermic or exothermic by actually calculating the energy taken versus energy release. If you take more than what you release, it means that you're in a surplus, right? But if you take less than what you release, then you're in a negative. So in this way, we can actually estimate whether a reaction is endothermic or exothermic. We can count what is called the bond energy. I can give you an example. So for example, this is the data of bond energy. You can see from many sources. Usually it's in the form of table. Let's say that I have reaction of methane burning. So CH4, oxygen, carbon dioxide, and water. The first thing that we need to do is to balance this. Make sure that the atoms on the left hand side and the right hand side should be equal. So one carbon, four hydrogens. So we multiply two here. Oxygen, two and two. So four multiplied by two. So if we draw this actually, yeah, you don't have to know to draw this. Some of the questions will provide the drawing for you. The shape is like this. Oxygen is O double bond O, but we have two. Don't forget. Carbon dioxide is this thing, and this, but we have two. Okay. Now we have to check all of the energy that is required to break these bonds. Here, energy will be taken to break the bonds. So we need to break one, two, three, four CH, and we need to break two O double bond. We see here that CH actually is here. And O double bond O is here. So this will be energy taken one, two, three, four, and this two. Wait, we're missing one information. So C double bond O, if I'm not mistaken, it's 803. Let's say that this is this. So to break the other bond, we need two. So we need this two times, and we need OH one, two, three, four times in order to create this energy release. So if we want to consider energy taken, the delta H, we would have to count energy taken. So 4 times CH415 plus 2498 minus this thing 2803 plus 4464. Now let's see. 1640 plus 498 996. Don't forget that this should be the total of everyone. 16, something like this. Therefore, we have this minus this. Or we will have negative, I think, yeah? 6, negative 8 to 6, let's say. Okay, so this reaction is considered to be exothermic. Now, if the question asks you to draw the energy level diagram, then we can draw neatly. Initially, let's say that the energy level starts from here. Then, oh wait, this is exothermic. Better to start a little bit higher. Then it goes, it needs a certain activation energy, then it goes down. This part here should be the reactant. So methane and oxygen, while this part here should be the product. So CO2 plus 2H2. And then you need to label that this here is the change of energy, which is negative 826 kJ. And here is the activation energy. So this is the complete diagram of this reaction, which is an exothermic. I hope that this video helps so you can calculate the change of enthalpy based on Boole energy and classify the reactions.